This lesson deals with Kirchhoff's current law, and you can find these notes in the ECE201 ebook in Chapter 2, starting on page 13. Before we talk about Kirchhoff's current law, we need to define one more term. A node is a juncture of two or more circuit elements. So what we've seen previously in this chapter are some circuit elements, the first one being a resistance, and then a voltage source and a current source. These have two terminals, and what we can do is connect one of those two terminals to other two terminal elements, and again, one of their two terminals. So the node is the point where they come together, but it includes all of the wires that come with that element. Now we're going to assume that those wires have zero resistance, and again, as an ideal component, just like the resistance is the ideal component, and the voltage source and current source. And we'll see later is that you can model real devices with idealized devices. Now in Chapter 1 we talked about electric circuits having two postulates, and that from those two postulates the properties of electric circuits will follow, and we'll be seeing this all throughout the course. The next postulate is called the conservation of charge. Simply stated, charge is neither created nor destroyed. The consequence of that is actually Kirchhoff's current law. The algebraic sum of the currents entering a node equals the algebraic sum of the currents leaving the node. Okay, now why would that be true? The charge that enters a node must leave the node since there's no place to store it and it can't be destroyed. Now this is true at every instant in time, and current is charge per unit time. So the current that enters a node must equal the current that leaves a node. And that would be the proof of that. Let's do an example. Here's an interconnection of 5 two-terminal elements, and these dots represent the connection to the wires associated with those elements and the wire that would need it to get to reach to the other elements. But that's not the node. What the node is all of this. The solder connection, the connection point, the wire itself, that's all a node. Likewise here, and maybe you should extend this one a little bit bigger in here. Something like that, maybe better, but you get the idea. It's just all of this is a node. So I'll call this node A, node B, and node C. All right, so we're going to apply Kirchhoff's current law to these three nodes. Let me just erase that. Now in the notes, I do something fairly consistently. I put the currents that enter the node on the left-hand side of the equation, and the currents that leave the node on the right-hand side of the equation. So at node A, I have nothing entering, and I have two currents leaving. Now this problem, I've assigned the currents. I'll later talk about how you might do that. So that means that 0 is equal to I1 plus I2. You can find these formulas at the bottom of this page. Let's go to node B. Okay, what's entering the node is I5, and here's I1. It's actually going to go through this element, come out the other side. So we've got I1 entering, and we've got I5 entering. And leaving is I3 and I4. So I1 plus I5 equals I3 plus I4 at every instant in time. So if we knew the value of some of these currents, we could then solve the equations for the remaining ones. In fact, we're going to do that in this chapter and talk more formally about it in Chapter 3. Let's do node C. What's entering the node is I2, I3, I4, and what's leaving is I5. I2 plus I3 plus I4 equals I5. And that's how you do Kirchhoff's current law. The currents that enter the node equal the currents that leave the node. The textbook uses dots to indicate connection points, and they're doing that really for a software package where they're going to use schematic capture. I'll talk about that in this course, but in a later course. Many people just use a single dot to indicate the node. So here's node A, node B, and node C in the previous example. I will basically use this notation throughout this course and all the courses that follow. Other schematic symbols throughout the notes in our textbook also. Let's explain these real quickly. Two wires cross and they're connected. We put a dot to indicate that they are soldered together or connected together. And of course here they're not. Also emphasize this even more by showing a little jump over the wire. Now if you don't have a very large schematic, this is not hard to do. But if you have thousands and thousands of wires, then just this notation is a lot simpler. I'll do mostly this in the course to just double emphasize that we're not connecting at that point. If you have a right turn or a corner, this means that the wire is just continuing. People tend to draw schematics with right angles and makes them look prettier, but it really means the same thing as if you just drew a straight wire at any angle. We also have connectors where we connect things together. We'll show the connector as if it were not connected, but it's really implying that this is connected, but there is a physical connector plugging one thing to another. So it's like a 1/4-inch jack going into an input stereo. Also have things that are controlled by other things. As an example is a relay. Switch is open and closed by some action. Or you can even think of a wall outlet switch as you flip the switch up or down, there's some external control line that's doing that. That's not really part of the circuit. It's some other external force. This can be electronic also. Looked at one form of Kirchhoff's current law, saying that the currents that enter a node equals the currents that leave the node. But there are other ways of saying the same thing. And our textbook uses another form of Kirchhoff's current law. Simply stated here. If the currents entering a node are taken as positive and the currents leaving the node are taken as negative, then the algebraic sum of the currents is 0. Why would that be true? If a designated direction of current is leaving a node, let's reverse its direction. And what you're going to do then is change its sign, as we discussed in chapter 1. Now, summing the currents, we have everything entering the node and nothing leaving. So again, what you've got here is a summation of terms that is equal to 0. This is handy sometimes in proving theorems where you have a 0 on one side of the equation. Either of these are really saying the same thing. Let's do the same example over. I'm going to show you algebraically what's going on here. So we're going to take all the currents that enter a node and basically subtract them. So here's I1 leaving the node and I2 leaving the node. So we're going to subtract those two or put a minus sign with them. There aren't any that are entering, and then that sum is going to be equal to 0. Really all we did was take the previous answer and move the currents from one side of the equation to the other. It's not an algebraic step, but in words it's said quite differently. Look at node B. So I've got I1 entering, I've got I5 entering, so they're just added, and 3 and 4 are leaving, and so I'm going to be subtracting those two. Node C, I've got 2 entering, 3 entering, 4 entering, 5 is leaving, so I'll subtract 5. I find this a little more confusing than the one we did previously, and in the notes for this course and the follow-on courses, I'll basically use that first form of Kirchhoff's current law. The currents that enter a node equal the currents that leave a node. This will be handy for proving theorems and another way of looking at things too. Both give you the same answer. So an example where we find some unknown currents. Suppose that I build this circuit and I'm able to measure the currents in some of the elements. We'll later talk about how you might do something like that. So unknown here, I2, I4, and I5. So let's see if we can solve for those. You might want to look before you leap here and try to find a node where you know everything but one of the currents. Then we can use Kirchhoff's current law to find the other unknown. Node A here, I've got two currents and I know one of the two. So the current that enters the node is I2. The current that leaves the node is I1. Well, again, the current itself can have a value, and that value can be positive or negative, as we mentioned in chapter 1. In this case, I2 is equal to minus 1 milliamp. Put all of our answers in this course in engineering notation with the proper unit. So minus 1 milliamp. So we go to node E now. Oh, I2, I know I3, but I don't know I4. Solve for I4. The currents that enter the node are none. The currents that are leaving the node are I2, I3, and I4. But I know the value of I2 in this direction is minus 1 milliamp. The current in this direction is 500 microamps, and I'm going to convert that to 0.5 milliamps so I can add or subtract these quantities. A little bit easier, I can do it in my head. And lastly, I4 is what I don't know. So adding those two together, I get a minus 0.5 milliamp, and I'm putting that on the other side of the equation. I get a plus 0.5, and I'm going to put that again in engineering notation, which is 100 microamps. Lastly, if I go to node C here, I know I4, I know I6, but I don't know I5. So I4 plus I6 are entering the node, I5 is leaving the node. Well, it's just that simple. And now let's see if we can solve the equation. From our previous answer, we have that I4 is 500 microamps, or 0.5 milliamps, and then from the schematic, we see that this was measured as minus 200 microamps. So you can write that as minus 0.2 milliamps, and that would equal I5. So adding these two together, I get 0.3 milliamps. Convert that to engineering notation, and I get 300 microamps. Just a note here, there are two signs associated with the things we were doing. One is the direction of current, and the other is the value of the current. So the current itself has a value, it can be positive or negative, and then the direction of the arrow is indicating the net flow of positive charge. But if we turn that arrow around, we then change the sign of the quantity. And this is Kirchhoff's current law.